want to tell you about the 1980 eruption of Mount St Helens because it was one of the first eruptions that made clear how important landslides were in triggering volcanic eruptions, and because the monitoring process that was ongoing at Mount St Helens was helping to predict the eruption that took place in 1980. In the foreground, you're seeing Spirit Lake and Mount St Helens in the background. Before and after pictures of Mount St Helens shows the devastation that took place after that eruption. You can see Spirit Lake in the foreground, and you see several things in the image. Not only is all the vegetation gone, either knocked down or burned, or both, but the summit of Mount St Helens is missing after the eruption, and you see a resurgent dome in the center of the crater. And Spirit Lake is covered in logs, trees that were knocked down, and other debris that was deposited after that eruption. Closer to the volcano, you can see that the immediate area surrounding the volcano, basically everything was destroyed. And this is in 1984, almost 4.5 years after that eruption. And a lot of the vegetation had not yet recovered. Prior to that eruption, and in between April 27th and May 17th, 1980, the monitoring that was being done by geologists at Mount St Helens showed several features, including a swelling of the volcano, particularly on the northern flank. And what you see in this image are lines showing how the side of the volcano raised up in elevation and pushed outward from the center of the volcano. And how this was determined was using LiDAR and GPS to show that the distance between a certain point and this landmark, Goat Rock, changed over time. And so there was a lateral distance increase of 18 meters in just that 3 weeks prior to the eruption. This is the bulge on the north flank of Mount St Helens that had developed in the months preceding the eruption. This is the feature that I'm talking about. And here's Goat Rock that was being monitored for movement. The sequence of events that led up to that eruption included not only a swelling of this northern flank of the volcano in the weeks just preceding that eruption, but a landslide that took out the northern side of the volcanic rocks covering the magma chamber that was building underneath. Once that pressure of this overlying weight of rock was removed off of the top of the volcano, that allowed exhalation of gases in that magma and an explosive eruption on May 18th. Shortly after that eruption, too, there was a lava dome that had formed in just a month or so after the May 18th eruption and persists today in the crater. And at 8:32 a.m. on May 18th, 1980, the eruption took place shortly after that landslide occurred. And you see in this image this dark cloud of ash that tells you there's new magma that's been erupted, and it's not just steam. There were pyroclastic flows that were sent down the flanks of the volcano. These are ground-hugging avalanches of hot ash, gas, and volcanic debris or other tephra. And those tend to follow topographic lows, so valleys or stream beds around the volcano. And they move at very fast speeds, up to 400 or 500 kilometers an hour, and they're extremely hot. So they can knock down and burn everything in their path. And certainly that's what happened in the immediate area around the Mount St Helens crater. Just before that part of the eruption took place, at 9 o'clock in the morning, there was a vertical eruption column of ash and volcanic gases that rose. And after 10 minutes of this eruption column rising, it had reached an altitude of 12 miles above the volcano. This map shows the area surrounding the northern crater of the volcano. And what you're seeing in these orange colors are a direct blast zone in the 5 or so miles immediately surrounding the crater and including Spirit Lake. That direct blast zone, everything was destroyed in it. That reached from about 5 miles to 8 miles around the volcano. Beyond that is a zone of channelized blast. So in this dark orange, that's where pyroclastic flows and any lahars would have destroyed a larger area around the volcano, so 8 to 19 miles out. And that's controlled by topography. As I said, the pyroclastic flows are following the low points in the topography. And then in the seared zone, in this more yellowish color on the outside, this area is an area where trees were left standing, but all the vegetation was burned. And the other thing that you can see in this diagram are the flow lines for the direction that the pyroclastic flows would have taken. This is the area of the direct blast zone. You can see the Spirit Lake in the foreground, and everything in sight is burned, and large trees, fully grown trees, knocked down like toothpicks. An image of what the direct blast zone looked like. Everything's covered in ash and other tephra, and trees just look like they're snapped at their base. Full-size trees here, and you can see people for scale. These are large trees that were knocked down. This is the edge of the channelized blast zone and the sear zone. So you see some trees still standing in the seared zone, but we've also got these trees that are laid down flat. So we're right at that edge. This is a deposit of that material that was involved in the initial eruption. And what you're seeing is about 50% gray juvenile dacite lapilli mixed with fragments of older rocks and pieces of wood from trees that were knocked down by that pressure wave. The juvenile dacite means that this is new rock that was erupted from the magma that had risen and erupted that day. Here you see more trees blown down and burned near the direct blast zone. And you have vehicles in the foreground, probably a geology field trip, parked alongside the road to look at the damage. This is a view from the channelized blast zone to untouched forest. And I include this because these are the topographic lows that I'm talking about, where pyroclastic flows would have followed and lahars may have followed as they poured out of the volcano and were pulled by gravity. Here's a map showing the area where pyroclastic flows in Lahar were laid down. We see again, there's the top of the volcano and the crater. In red are the pyroclastic flow deposits nearest to the crater. And in brown, we have the avalanche deposits that preceded the main eruption, as well as the Lahar deposits that extended even farther than the pyroclastic flows and landslide deposits. These lahars can reach many miles from the volcanic center, and they're fluidized tephra, ash, from either being laid down in streams or from melting snow or ice that were on the volcano and then rushing down, taking large boulders, trees, cars, cabins, whatever with them. Pyroclastic flows can actually be erosive and remove older deposits as they move down these river valleys. And in that respect, they can remove part of the geologic record that we have for these volcanoes. And so we might be missing information about large eruptions in the geologic past because some pyroclastic flows can be erosive. So it's removing some of the evidence, and therefore we might not have the best idea just how often these volcanoes can erupt. Here's a view of the Lahar that came down from the crater center in March 1982, so a couple of years after the 1980 eruption. But it's easy to see because the Lahars are so dark compared to the snowy backdrop of the volcano. And you also see a steam cloud, the white cloud that's erupting from the crater center. We know that's not an ash eruption because it's not dark gray. Here's an example of Lahar damage, and all the mud you see everywhere in this image is a result of a Lahar deposit, and the damage that you see to the trees and to the cabin are also a result of the Lahar deposit. You can see this line of white on the trunks of these trees are showing you how high the mud and water reached. This hot material that is erupted out of these volcanoes, when it gets deposited onto ice and snow, you can have a phreatic eruption, an explosive eruption, where you're taking the snow or ice from the solid state immediately to steam, and it erupts in these explosion craters that are very large indeed. These are full-size tree trunks that were knocked down during the eruption. So just imagine that those are at least 100 feet tall. So these explosion craters are very large indeed. This shows the path of the ash cloud that came out of that initial May 18th eruption in 1980. And what this is showing you is that at 9:15, the ash cloud had reached almost to the eastern Washington border. And by 5 o'clock that day, it had reached out to Montana and across Idaho. This diagram is showing you the direction of wind that was blowing that day and the height in the atmosphere of that ash cloud. Most of it was at 10, 12 kilometers height and blowing up to 120 kilometers per hour. If we step back and look at the larger extent of this eruption, the ash cloud reached as far east as Minnesota, and those deposits were quite thin at the time. Those were less than a centimeter of ash that was deposited that far east. The main part of the eruption, up to 12 centimeters, was in the eastern Washington, central Washington area. Here you can see the different directions at different heights in the atmosphere where the aerosol cloud that was part of the volcanic gases that erupted that day, the direction that those reached. So the material that was higher up in the atmosphere, 20 kilometers and above, was headed west-northwest, while the material that was lower down in the atmosphere was headed across the Atlantic. This is an image showing the lava dome as it existed 25 years later. And you see the steep-sided lava domes that are erupting. These are rhyolitic lavas, indicating high silica content of the magmas feeding this volcano. And you see a steam cloud erupting. Again, it's white, so it's steam. There's no new magma involved. But this volcano is still very much active.